In this video, I'm going to discuss another interesting problem, which is commonly known as flood field problem, but there are also different variations of it, which I shall discuss at the end of the video. And let's see what the problem is. So you see on the left side of the screen that there is a two-dimensional grid which is filled with different numbers, and these numbers each represent an individual color. For example, 0 is one color, 1 is another color, 2 is a color, 3 is a color, and in the grid the cells are connected. For example, each cell has 8 neighbors except the cells at the edge. So for this particular one, we have neighbors like these top 3 are neighbors because those are reachable upwards or diagonally, just one step. And this one is a neighbor, this one is also a neighbor, and these 3 are also neighbor. All the middle cells, they have 8 neighbors, except say this corner cell, it has only 3 neighbor, or this cell, it also has only 1 2 3 4 5 neighbors. So I hope you understand what it is about. I shall be given a position, a starting position, and a new color, and starting from that position, I need to find whatever cells are having the same color, and I need to mark all those cells, connected cells, with the new color. So if I am given this grid and also this position and this color 4, so which one is 2 3? If I start from here, then this is 0 1 2, then this is 0 1 2 3. So I shall start from this cell 0 1 2 3. Yeah, so I shall start from this cell and then find all the neighbors and all the cells that are connected to it, and then mark it with the new color. So this one, it has 8 neighbors, and among those 8 neighbors, these two, and this one, sorry, this one is not a neighbor yet. So these are connected, right, directly, and then I can do the same thing again from here. So from here, this I get one new thing here, and then if I do the same thing from here, so you get the idea that, so this one is connected, so I'm just making, then this one is connected. From here I can go here, and also this cell, and this is also diagonally connected to this one, and from here I can go here, and here. I think that's it. So all those cells with 1 needs to be replaced with the new color, which is 4. You can see in the second grid. But what we don't need to do is, for example, this one, it is 1, but we cannot replace it with 4 because this cell is not reachable from the starting position, which is this one. And now if you had the idea of just using a nested loop and check if the cell is 1, replace it with 4, this won't work. I have seen people attempting this approach, so which is not really the right approach. And there are standard ways of solving this problem. So if you are already familiar with graph searching algorithms like breadth first search or depth first search, which is called BFS or DFS in short, you can use either of the algorithm to solve this problem. But if you are not familiar, or if you heard about the algorithm or studied those algorithm long time back and no longer remember, don't worry, we shall develop the solution step by step. So let's start. So what we can do is we can start writing a function. Let me change the font. Color grid, which will receive a grid, a position, and a new color, and it will return the new grid, or it can just change the grid inside. And now what we need to do, for example, say with the starting from the position given in the parameter, we can find all the neighbors. So for node or cell in find neighbors grid position, then if cell has got the same color, and if you are worrying that what kind of Python code I am writing, I am not really writing Python, I am just writing this pseudocode first and then we shall convert it to the Python. So if the cell has got the same color, then what we shall do is paint the cell with new color, and from here we shall just return. And what we did so far, so we started from the position given in our example, which is 2 3, and which is this one, and then using a function find neighbors, we can find all the neighboring cell. And at this point I don't know how to implement the find neighbors, we shall figure it out later, but let's assume that it will return us all the cells, and we are here looping over each cell and which are neighbor or reachable from the position. So the find neighbors is a function which takes the grid and one position and it returns the neighboring cell. And if the cell has got the same color as grid POS, then we shall paint the cell with new color. So if we just do this, we shall end up with like 4 4 4, and this one is also neighbor 4. And of course we all can now paint grid pass with new color, and then we can also change the color here to 4. So we only solved the one part of the problem, right? We didn't solve the whole problem yet. But if we can repeat the same process with the neighbors, for example this one, so if we find that, okay, so this is the neighbor, and again change it to 4, and then we find, okay, starting from this 4, this is a neighbor of it and this is another neighbor, so we just convert it to 4 and 4. And if we continue like this, then we can end up painting all the connected cells with the new color. And now what we need to do, we must find a list, right? Or we must build a list where we can add the neighbors as we explode them, and then from this list we shall continue picking one cell and find its neighbors and then put the neighbor in that list again. So let's assume that I name this list Q. Initially this is empty, and then what we can do is Q dot append pos, and if the cell has got the same color at grid position, then what we shall do is Q dot append cell, right? And we need to continue this, so we shall write a loop, and then this will happen inside the loop. And what we did at first we just put one item into the queue, and so we need to take this item from the queue. Say we can name it like pos, though we shall change the name later because I have already used it somewhere, queue.pop. So it will get the first item, find all the neighbors, and if the neighbor has got the same color as grid, we shall append and then paint it with the new color, and then paint grid with the new color. Now there is another problem. So when we painted this with 4 and then we start with this cell, then when we look at the neighbors, none of the, I mean, say when I find a new neighbor with 1, which was the original color, but now I can't match whether it has the same color as position, right? Then probably we shouldn't do it here. So if we do it here, then the cell has the cell has got 1 and grid position has the color 4, so they won't match. So I cannot tell that this is uh, our desired cell. So we don't need to paint it here. We shall only paint at this position where I have explored all the neighboring cells, and I have checked whether they have the same color as mine, and if yes, then I put this into the queue or into the list, and then only then I shall paint it with the new color. So this is all right, and we don't need to do it. Now we need to care about another condition, which, so for example, say this one, it is a neighbor of this cell and it is also a neighbor of this cell, right? So it may come into the list twice, but there is actually no need to explore it twice, because unless we can end up doing a lot more work than required. So if I have already uh, found this cell, for example, when I was exploring the neighbor of this cell, of course I shall get this 3, right? And then again, when I'm getting the neighbor of this cell, I shall again get this particular cell, but I don't need to count it twice or more than once. So I need a mechanism to keep track of this. For that, let's uh, create another list, explored, and it should be same size as grid, and initially it should be false, that I haven't explored anything yet, or we can use either false or we can use 0. So let's use 0 here. So we need to build the explored list like this for item, for row in grid, explored dot append 0 into len of row, right? And then we shall get the 2D grid of the same size, but everything should be filled with 0, right? And I think we can start writing our code now. So this queue is fine. This is already Python. This is also Python. And this while true, I just wrote it to show that we need a loop here. But how long we need to continue doing this? We need to continue doing this till we have at least one item in the queue, which means we have added this item while we are exploring neighbors from the cells. And as we have added this item, we also need to explore from this item. And once there is nothing to be explored, then the queue should be empty. So while len queue greater than 0, then I shall do queue dot pop. And here we can actually write like this, xy. So it will return a tuple, because the position is a tuple we already see here. And then we shall implement the find neighbors later. We send xy here, and if cell has got the same color as grid and the cell is not explored yet, right? Only then we shall append. So if I translate it into Python, then if grid xy and the cell should be nx ny is cell, so we do like new x new y. If grid xy is equal to grid nx ny and explode nx ny is false, only then we append the cell into the, we append like sorry, nx ny, and then we paint the original one from where we explode everything with the new color, not the items we added into the cell. So what we shall do here is grid xy is new color, and then we just return. And now let's implement the find neighbors. And before we implement the find neighbors, let's examine our code and go uh, step by step to make sure that we got everything all right. Yeah, so here we have just created the explode grid and marked everything with 0 initially, and this is our queue. Here we are adding only the starting position. Then while we have at least one item into the queue, which means the length of queue is greater than 0, then what we are doing are getting the first item from the queue, which is xy. And as we are storing a tuple in the list, so we can get it like this in Python. And then we call a function called find neighbors, and it will find all the 8 neighbors if it has 8 neighbors. If it doesn't have 8 neighbors, then it will find whatever neighbors it has, and then it will come as a tuple. And that's why we are actually, you can write nx ny here, just make the code short. And if grid xy has the same color as the grid nx ny and it's not exploded, then only then we shall append it into the queue, I mean adding at the end. And what we are doing here next is just make the grid of xy with the new color. We're just changing the color. I think this is good. Now we need to implement find neighbor function, which might be a bit tricky if you haven't seen this technique before. So if we know a position, for example 2 3, how can we know that what we need to do? Actually, we need to find all the coordinates of the 8 points, right? And if you see that, okay, so this is 2 3, so this particular item is 2 3, so its neighbor, this one is 2 4 and this one is 2 2. So we can add 1, we can subtract 1 from the x axis, and y axis, and we can get two items here. Then similar way we can find 3 items of the previous row and 3 items from the next row. So all we need to do is keep a list of 8 tuples that we shall add to our xy to get into this. If the idea is not clear yet, you will see very shortly from the code. We find neighbors. Now we need to keep a vector, which, and now say if I am at one particular point and if I want to get to the next one, shall have 0 plus 1, and the previous one should be 0 minus 1, then the upper left should be minus 1 minus 1, then the one above should be minus 1 0, then minus 1 plus 1. Cool. And then for the next one it should be 1 minus 1 1 0 1 1. I think I have 8 items here. 1 2 3 4 5 6 7 8. Yeah, so if you just add this to the xy, which means that you shall add the first item to the x and second item to the y, then you will get to the next cell of the same row. This is the previous cell of the same row. If you add minus 1 to the to x and minus 1 to y, you will get from the previous row, the previous cell, the previous row, same column, and this is previous row, next column. So this is great. Then for item or dx dy in d nx ny should be x plus dx. So dx is the change, right? How much it's changing, y plus dx, and we are just using plus here because if we need to subtract, we have already put -1 here, so it should be like y minus dy actually. And now we need to do one more thing. We need to make sure that we don't fall off the grid. For example, for the first row, if we try to go to the previous row, no such row exists, right? So we need to check that nx is greater than, so we need to find row and column len of grid, column should be len of row. So this is basically the dimension. So if nx, and if it's starting from 0, then if nx should be less than row and nx greater than 0 equal to 0 and ny less than column and ny greater than equal to 0. Only in that case we shall have append nx, ny, and here we can return this list. And we need to initialize it here. So this is a bit tricky way of doing it, but if you really understand the code, we can actually do without using this vector, right? In that case, we need to write a bit more code to find each neighboring cells, but here this is a more concise and to me it's more beautiful approach to do it. And here we are just making sure that we don't go beyond the grid, and that's it. And now if you are not familiar with BFS or breadth first search, so what we did here is called breadth first search. We have searched the grid with using breadth first algorithm, but for this particular problem you actually don't need to remember BFS, because if you just figure out the idea of how it works, that would be great. And now let's try to figure out what is the time complexity and space complexity, right? And say if the grid has row, column, I mean this is the dimension, so this is the row by column, so this is our grid, right? And then our memory space complexity is order of row into column, because we have used this explode array. Oh, we also need to do one more thing here. We need to mark like explode nx ny 1. So we have already exploded, and we need to do it here as well for the initial item. So the xy should be, and now regarding the time complexity, we are actually visiting every cell once, and in the worst case, say every cell is painted with 1 and we need to convert it to 0, then using this loop what we are doing is we are visiting every cell, and actually we are visiting every cell once, because using our explode grid we ensure that we don't visit a cell twice. So our time complexity is also order of row into column, but here is a catch. As I used Python list here, when I do like this q.pop, it's actually order of n instead of, this is not order of 1, this is order of n. So this q can grow to the size of row into column, and as we are again popping every item, so the time complexity will be row into column into again the q size, and q.pop is on, and here n is row into column, so row into column. So this is not really very helpful. So what we can do here is we cannot use plain Python list to do it. Fortunately, there is a double-ended queue or deck implementation is Python. So from collections, import deck, and then instead of using like this, we shall introduce it, initialize this with deck. So it becomes a double-ended queue. The advantage of using double-ended queue is this operation is order of 1, but in deck it's called uplift. So if you want to implement double-ended queue from scratch, it will take you a lot of time. But as Python has already implemented this, I believe that if you use C++ or Java, you should find the implementation in C++, HTML, or any of the Java libraries. So you can directly use that. And just we need to make sure that this is order of 1 operation, and then we are good. And this same problem can also be solved with BFS, which I shall show in another video. So at the beginning, I told you that there are some variations of this problem. So what are those variations? Sometimes they will tell you, okay, so they will give you the grid and give a starting position and target and tell you to find the shortest path. You can of course use BFS in such grid to find the shortest path, because BFS can find the shortest path if there is no weight in the paths, like in this kind of grids where each neighbor has one cell distance. And there is another variation, which is like they can tell you to find the number of islands. So this is a grid of 0 1, and say 0 means water and 1 means land, and if the ones are connected, so those are islands. So they can give you a large grid and ask you to find how many unique islands are there. That there you can also use DFS or BFS to find it. And as I said, I personally faced this problem at least twice as a candidate while I was interviewing. Though I don't ask this type of questions to the candidates, but you never know, you can face this kind of problem, and it's better to be prepared. Otherwise, sometimes it's hard to find the solutions during the interview. So I wish you all the best, and we shall see each other in another video.